Okay, welcome to part 3 of this video. Basically, I'm going through the series of Ohm's law and showing you how the three elements work: voltage, amperage, and resistance. And remember, voltage is pressure, also known as electromotive force. Amperage is the flow of electrons. That's the current. Okay, again, we measure that in amps. And then there's resistance, the opposition to the flow of electrons. We measure those in ohms. So last video I left off talking about, I kind of abruptly ended because running out of time in my other video about current. So I wanted to start off with that in this video. I drew the circuit again. Here is a parallel circuit, parallel being the two loads with their own power and ground source. Two incandescent bulbs matching over here, spliced right here. And basically the last part of the video I was saying is that if we want to measure current, all we got to do is separate one point and a circuit, and that gives us 2 points. Oops, move that wire. It's going to give us these 2 points right here. So here I have hooked up to amperage, and I could put my meter in series between there and here, and that's going to give me my amperage. Okay, so we block out one of these lights at least for now. Let's see if we can block these out, cut out the glare a little bit. So right there on this bulb circuit right here, this branch, this one over here, I have 0.31. So right here, I split this off, and my ammeter is now right there, and I measure 0.31 amps. Okay, so if I take that, and notice how I take out that circuit, and only one branch goes out because it's in parallel. So I open up this branch, only that one is affected. Now let me go over here, let me open that up. Let me put these right here again, so you can kind of cut down on the glare here. Now if I put my ammeter in there to here, and I hooked it up right here, I'm going to get very similar. See, 0.30. So over here, my ammeter is right there. I am measuring 0.30 amps. Okay, and if I take this out there, like that, and let's say it's go up here to this, to right after the switch. Now both of them go out because it's affecting both. And again, I'm going to hook up my ammeter right here, and then up here to the top. Let's see, let's go this way. So now the current, if I follow it, it's coming through this fuse, coming up through this wire, going through the switch, going through this red lead, which goes down through my meter, through this black lead, back up to this black lead, through this down to the splice, and then over to both loads, and then back to ground. So the equivalent on the schematic is going to be just after here. So we're measuring amperage right there. Okay, this is the series part of that circuit. So right here I have what, 0.63. So 0.63 amps. Basically it's the addition of these two. So total circuit current, this is an Ohm's law rule, total circuit current is equal to the sum of both of these branches. Okay, so and that's kind of basically why you can't keep adding circuits. Like I can't just add another circuit here and say I bought another light off eBay or something. If this is another 0.31 amps, let's say, what happens to this 0.63? It's going to go up. Okay, so anything from this splice up is going to get loaded. It's going to have more current going through that. Because again, the total circuit current is equal to the sum of each branch. Okay, so if you were to buy, let's say if you were to design a circuit, and this is basically Ohm's law, let's do it this way. So Ohm's law can be represented like this. You have E over I, R. E is electromotive force, I is intensity, R is resistance. I know that seems kind of weird. We also draw it this way. Okay, V, which is voltage, over AR, but I've also seen it this way. V over A, and then the omega symbol. This one's probably the most common one you get. Again, this is electromotive force, that's E. I is intensity, that's for current. R is for resistance. I remember this as the eagle flew over the Indian reservation. And what this is showing us is a mathematic formula where basically V is equal to A times resistance. A is equal to V divided by resistance, and resistance is equal to V divided by current. You can draw it like this way. V is equal to A, R, so that's resistance. A is equal to V divided by R, and then R is equal to V divided by A. So all kind of a mathematic formula. It's kind of hard to explain in a short video, but basically everything is working off kind of like a teeter-totter. If voltage was my fulcrum right there, and then let's say this is amperage and this is resistance. As amperage goes up, resistance goes down. They're kind of inversely proportional. If my resistance goes up, my amperage goes down, as long as voltage is constant. And that's in relation to the automobile industry. So what I can show you here is why this matters also is if I look at wattage, so watts, which is work being done here, power, that's voltage times amps. Okay, so voltage times amps, let me turn the circuit off for a second. Voltage times amps is equal to watts. Okay, so we can have that voltage or watts is equal to VA. Okay, so why does that matter for us as a technician if we're designing the circuit, etc.? Well, basically, if I were to buy, let's say, I don't know, some type of bulb I want to hook up to my car, or something that has a certain amount of power, I would have to use this formula to figure out, because the box would tell me my wattage. If I open it up, let's say it's got a 55 watt, whatever it is, okay, 55 watt. My voltage, let's go nominal, let's do 13 volts, because it could be 12.5, it could be 13.5 on a car. So if I'm going to figure out what kind of circuit I need to design, I take that 55 divided by 13, and I'm going to get 4.23 amps. So whatever that load is 4.23 amps. Let's say it's a bulb. If I draw my circuit here, I don't know what size fuse. This is a question mark right now. If I come in right here, I have my switch. Comes over here. Here's a bulb that I installed, another bulb, or I'm adding a bulb. Okay, so here's my circuit. I know that they're 4.23 amps a piece if they're all the same. And we know based on the previous we just talked about, total circuit current is equal to the sum of both branches. So if I have 4.23 plus 4.23, what do I have up here with this fuses? Yep, I'm going to have 8.4, 8.5, let's go 8.5 amps. So let's find us, the next comparable fuse. Let's call it a 10 amp. So in here we would put a 10 amp fuse. And now we designed a circuit purposely and designed it so we have appropriate fuse. Now what size wire? Well, we would take to the American wire gauge, find out online, look up how many feet you're running, this 10 amps, and then you can figure out, okay, I have 10 amps up to this splice. From there I go to 4 amps, and I can kind of step my gauge into something smaller, which is a higher number. I know that's another video. But basically this way you could design a circuit off some type of accessory you bought. Okay, that's a whole nother type of video, but we're just talking about Ohm's law as a whole. Back to this circuit here. Basically, again, this is a parallel circuit. Each branch is separate from each other. So, yeah, that's amperage. So now if I want to talk a little bit about resistance before this video ends, let me take this branch off. Let's do this. So I want to show you a little bit about resistance. Now resistance can be a little bit harder to work on, to use in the car. It's kind of because basically on the circuit, when you're measuring resistance, you have to do two things. You have to unpower, you depower the circuit, it has to be off for the ohm meter to work, and you have to isolate whatever it is you're measuring. That's because the ohm meter is going to send out a small voltage out this red wire to the black wire and kind of measure the current using what we talked about here on Ohm's law earlier. Whoops, where'd it go? Right here. Using Ohm's law, it's going to use this mathematical calculation to figure out the resistance of whatever it is you're measuring. Okay. So the reason why that doesn't help us as techs is what's the purpose of the circuit? The purpose is to turn on this bulb. I want it to be on. That's when I'm measuring it. And basically, what I'm going to show you is proof why we can't dynamically measure resistance. Okay, again, we're going to have to measure it statically, which is the circuit's off. So if I take this, I have to turn it off, isolate the circuit, which means disconnect between what I'm measuring, and I measure the resistance of this. Okay, I'm going, oops, maybe it'd help if I switched it over, right? So if I'm going to measure the resistance of this bulb, okay, turn off that beeper. If I measure the resistance of this bulb, I'm going to measure right about 3 ohms, okay, 3.7 ohms. So let's do it this way. If I take and we do Ohm's law, I'll prove to you why there's only a few instances I would use resistance as a viable check. Okay, so we had it with 3.3. I think I already forgot. 3.3-ish. I think it's bouncing around. Well, let's see, 3.7 stable. Okay, so we'll do 3.7. 3.7, and we measured our voltage. Let's measure the voltage again. Make sure we're on DC. Okay, there we go. So ground. Let's see what kind of voltage we have. Oops, I gotta turn my switch on. Probably help. 12.09. So if we have 12.09, and if we take 12.09, let's do this 12.09. My calculator out. Divide it by 3.7. That gives us 3.27 amps. Okay, so if we were to switch this baby over to an ammeter, again, let's move this over here, turn on my light, hook that up, and now let's become part of the circuit. I'm going to jump these two and see what we get. What do we get? Okay, we are getting, oops, I got to switch over to DC. This is a new meter. Sorry, I lost my other one in the campfire. So 30. Right, we got 0.30 amps. It's 300 milliamps. That's a far cry from 3.27 amps. We actually got 0.3 amps. So let's take this into our Ohm's law. And we know we had 12.09. Let's do it the other way, 0.3. So now, let's take a look. 12.09 divided by 0.3. It's about 40.3. 40.3 ohms. Why the discrepancy? So either I have my ohms off or my currents off. If it's Ohm's law, why is it off? Well, that's because of heat. So heat creates resistance. That's why a dynamic test is better. That's why we measure voltages. When I was showing you before, on the we were doing a voltage reading. There's only a few instances where reading resistance is a valid test. One of the which is like switches or shorts to another circuit or short to ground, isolating stuff. So here I have like volume control switches. I have some back probes here. So this is something that I would use, and I drew a circuit to kind of explain the, let's see, let me get this one out. There you go. So basically what's happening with two wires, the computer, the audio control module, can take two wires down and through these series of resistors and switches. Every time I operate a switch, it's bypassing different resistors, and that measures or that changes the total current going to this computer. I can use my ohm meter to measure these, always back probe, never front probe, and that's going to give me an accurate reading that I could check each switch based on the schematic and make sure I get the appropriate reading. Okay, that's one thing I could do. The other reason I would measure resistance would be if I had two circuits, let's say, you know, like this, and then they come through a switch, bulb, whoops. Okay, so I have that. If I had, you know, a series of connectors like this, in here like that, if I had either this one connected shorted to here, or something to ground blowing it up, I can isolate the circuits, disconnect them all, hook up my ohm meter to either ground or to each other circuit, and I'm going to basically hook it up to each connector in line here, and then check it for shorts to either another circuit or short to chassis ground, chassis power, and I'm going to disconnect, go down the line and disconnect one connector at a time or go up until I find out what section. I'm going to either move my meter down. I can move it down. It's kind of hard to explain. Every tech has their own way. You're going to find your own way. You move either move the leads down or up, looking for which section is shorted to ground or the other wire. Okay, So that's basically it for this